So let's start. Today I wanted to, first of all, to talk about the Zariski site, which is one of the main examples of sites or various flavors of sites on affine schemes are chief examples of, well, basically topos theory sites. It's the origins of it's the very origins of the concept of topos. So let's first of all discuss what we're dealing with. So let K be a commutative ring. Then we want to study various varieties over K. So we consider an ideal inside of a ring of polynomials infinitely many variables. Then we define a variety corresponding to this ideal as a set of all points of homomorphisms from this algebra to the field K points. And one may be tempted to work with this definition of a variety. However, it turns out that a more fruitful approach is to consider instead not varieties as defined like this, but algebras themselves. So the reason for it is that it's often the case that the variety is empty. However, as an algebra, it's non-trivial. So for example, clearly, if we consider points, then, if we consider, for example, a variety like this, then it's empty. However, it's non-trivial when regarded as an algebra.
Grisha, it's probably R of X and Y.
Yeah. It's non-trivial when regarded as an algebra. Thank you for the comment. So what we're going to do is we're simply going to consider algebras. So finitely presented FP algebra, finitely presented algebra is a quotient of the ring of polynomials, infinitely many variables by an ideal generated by finitely many polynomials. Obviously, when we're dealing with, say, K equals to C, the latter condition can be dropped because the ring is Noetherian. However, here, since we don't have any information about the ground ring, we have to assume that the ideal is finitely generated. So those are polynomials. Okay. Now we're defining category KL of P as a full subcategory inside of K algebras generated by finitely presented K algebras. So unlike what we have over complex numbers when we're dealing with usual varieties, here we can have nilpotents, which correspond to small deformations of the structure of our variety. Okay, so in order to define Grothendieck topology, we need a notion of a covering, which we will now produce, emulating an approach to usual coverings by principal open subsets. So I recall that in classical algebraic geometry, principal open subset is a complement of certain, say, curve in a variety, and coverings are considered as union of principal open subsets. So unions of principal open subsets. So we will try to emulate this approach in abstract setting. Let's do this. So we have a set of elements which corresponds to this set of hypersurfaces inside of the whole variety spectrum of A. I'm saying this informally, of course, but the idea is clear. We want a condition that intersection of all hypersurfaces is empty. Once again, and this is an informal formula because we obviously don't have we don't consider them as true hypersurfaces because, as I said earlier, their intersection may be empty, but as a variety, it may be non-trivial. But still, the idea is that this condition could be replaced by a purely algebraic one. We just need to say that unit belongs to an ideal generated by all A1, etc., AN. Yeah, so that's the condition, and that's precisely the condition that principal open subsets cover the whole spectrum. Okay, so now we construct Grothendieck topology. By considering as its basis formal duals. So we construct Grothendieck topology on the opposite category of finitely presented algebras. The opposite category because varieties live in the opposite category of algebras. And so the covering of an algebra is a formal dual to the following family of maps. So this is the localization morphism. Note that localizations are themselves finitely presented algebras for the following simple reason. Each of them can be represented as a quotient of ring polynomials in one variable by one relation. So we don't go outside of the category of finitely presented algebras when we're taking localization. Okay, so now I formally define the basis of Grothendieck topology on the Zariski side. So is given by it's given by these coverings, and I want to recall the axioms for the basis. So that we had 3 axioms for the basis of Grothinger topology. Following 3 axioms. First of all, isomorphisms. If we had an isomorphism from D to C, then one element set consisting of this isomorphism belongs to D of C. Second condition is that if we have a family in K of C, and we have any morphism D to C, then the pullback morphisms belong to K of D. And finally, the third axiom is that if we had covering of each element of a covering, then we can produce a finer covering. So these are axioms for the basis, and we're going to check that what we defined for Zariski site is in fact a basis of topology, so it's in fact a site. Okay, so let's verify these conditions. So let's start from the first one. The first one is that isomorphisms belong to our basis. So the only isomorphism we have is A isomorphic to A, because yeah, because we're considering quotients of ring of polynomials, therefore if we have, okay, I don't think that, so no, okay, it's really trivial. So if we have an isomorphism, then by definition of our topology, it belongs to K of A. This is really this is really trivial. So it's just an assumption that we make from the start. Less trivial thing is that we need to check that under pullbacks, we're still getting coverings in the sense of this localization families. Okay, so pullback in KL opposite corresponds to forwards in the initial category K out. They in turn correspond to tensor products. As if A1, A, are elements such that the unit belongs to A1, AN, and H is the morphism in the opposite direction of algebras, then one belongs to H1, H, AN, because H of one is just one. It's a unit of morphism. And we have an isomorphism of algebras. First, we have a push-out diagram. Push out. So let me draw the diagram. Okay. Okay, so what we've proven is that we needed to check an axiom that pullbacks of covers are once again covers, and we did it. We just considered a pullback along map H, which is dual to certain morphism in the opposite category. And then we've proven that when we pull back, we in fact get a push out in KH, and therefore we get a pullback in KH of LP. Okay, that's great. Now to the most laborious part of our conditions is that's about transitivity. Okay, so 3 is transitivity condition. Assume that we're given covering family Assume that we're given a second covering family which covers all of this localized algebras. So we know that Cij belongs to this localization, and we know that 1 belongs to the ideal generated by Ci1, etc. Cini. That's the condition on a covering. Thus, each Cij can be represented as a fraction Aij Ij, where Aij belongs to the original algebra. So inverting Cij inside of in AI minus 1 is equivalent to inverting Eij. And so we have the following diagram, the following covering family. What we really need to check is that this thing here actually provides us with a family of elements such that Ibij, an ideal generated by Aibij, contains 1. How are we going to do this? Well, we start from observing that this element that this family of elements generates an ideal which contains 1. So they generate the whole ring. This is happening inside of a localization by the element AI. So these elements can have certain denominators. So we now can multiply by these denominators, and what we'll get is that AI in a certain large power ki belongs to AI bi1 AI bi and I. Since one belongs to a deal generated by AIs, we know that there is a certain linear combination partitional unity if you want. And so we can choose k larger than m times maximum of ki's, and we will get the following. So 1 is equal to pi ai to the power of k, and it belongs to ai k1, a1 k1, an kn, which in turn belongs to the ideal which is generated by ai bij for all ij. Thus, we've shown that A2 j minus 1 is in fact cover. Which we needed to prove the transitivity at some. So, yeah. So thus we've shown that we have a site which consists of all finitely presented algebras and covers which are dual to families of maps induced by localization in a single element. So that's basically all about the Zariski site. We will return to it once more when we will check that there is a canonical structure sheaf on this site. But outside of this, I think that's all that I wanted to say about the Zariski site. So now we can move on to sheaves on a site. Okay. So let's see, be a small category. J is arithmetic topology. C. And so a pre-sheaf is just a functor from opposite of C to sets. E is a pre-sheaf. C. Well, obviously it should be a J sieve, so sieve which belongs to J. Then we define the following notion. So a matching family for S system. The function is a function which takes the function on S, which maps each f from D to C S to XF in P of D, such that XF, when we apply G to XF, we get XFG for any G from E to D. So apply, I mean pull back, of course. So here, so yeah, this is an arbitrary in C, arbitrary morphism in C, FG in S. Such that S C before and FG is G. Okay. So an amalgamation of a matching family so basically what we're trying to do here is we're trying to emulate the condition that we have an element, say a function on each open subset. However, instead of open subsets here we have morphisms. And we're trying to collate it into one element on the union of open subsets. So amalgamation of a matching family is X, which belongs to P of C, such that when we pull back this X to each morphism F in the C, we will get XF. So P is a sheaf if for each matching family the amalgamation is unique. Okay. So of course this should hold for any C and C and all S Sheaves. Okay, so recall that C on C is just a subfunctor of the representable functor home to C. which is precisely the value of the unit embedding on C. So what is a matching family? Well, a matching family is just a natural transformation from S to P. Okay. Thus, reshape is a sheaf if and only if for any covering sieve we have the following extension diagram for any covering sieve S. C and any S to E, we have a unique extension. So this should be a commutative triangle. Okay. So in other words, P is a sheaf if and only if for any covered sieve S C, sorry, C inclusion from S to YC induces an isomorphism Okay, I think that now it's a good time to make a break. Let's reconvene in, say, 5 minutes. Okay, pause the recording. Here. So the thin condition on a sheet can be also formulated using the equalizer diagrams. So diagram. object in C and find as our C. Background. No, let's do. And we have pairs of impossible marches. Here we have main of G. Values beyond these domains. Okay. So this is sometimes a more commonly used definition of a sheaf. We just write this equalizer diagram and we obtain condition that the sheaf is a sheaf. Let me say a bit more about this diagram. So E on X is equal to the following in S and this is the same as take P of F on X. Okay. So E is just P of X just F X. So we actually can require that P would satisfy this equalizer condition only for one C, say S. So if satisfies condition, then we would say that satisfies the sheaf condition with respect to S. Okay. So if be a basis. If basis, we describe it purely in terms of the spaces. Okay, so inside of the spaces. The elements in each of PCIs. So phi is a match family. With respect to J 9 where E1 are projections which come from the following folder. Amalgamation. Family. Yeah. You see, such that x of phi equals xi. Okay. So let me formulate the following important proposition. E E E So J is a growth-index topology generated by K. There is a unique information. Image effect. Similarly, we have reformulation. Leave. Basis. Origin diagram. Yeah, is in the coils. Okay. So I will omit the proof of this proposition since it's technically challenging, but I will give an example. So we will once again use our very common source of examples, that is category C, which is equal to O of X, where X is the logical space. And we can consider a sheaf of y-valued functions. So we don't yet know that it is a sheaf, but if Y is a topological space, then we can consider all continuous maps from X to Y, and we can restrict those to any open subset maps, and we will obtain a sheaf on a category of open subsets in a topological space. This example can be generalized. Let C curly be a certain topological site, for example, site of CW complexes or countable Hausdorff spaces. Certain spaces. With the voucher. Then for a by this category, we have a representable functor. Adding Basil. Yes, so it is a sheaf. Why it is a sheaf? Well, basically because if we have twice, which is a covering of cover of this X, then in family functions, collates into uniquely defined function. Now, okay, so that was one example. Sheaves on the site, a rather trivial one. Now I will move on to less trivial example, which involves a Zariski site. So deserves more successful. So, by a kernel integral to k ouch to finally represent k ouch. And that cross-conjugate topology be defined as before. tools of families, localization morphisms in one element. And we require that A1 is that AN contains 1. Then we have the following functor. The category A op to set. It just maps an algebra here to underlined set. Okay, we want to show that this functor is in fact a sheaf. To check that it is a sheaf, we will use the condition on a sheaf in the form of equalizer diagram. So we need to check that for any condition, for any cover by principal open subset, which is this cover, we have an equalizer diagram like this. Okay, so we know that J is isomorphic to the product. So this thing here is a pullback A. One J minus. Let's show that this is indeed an equalizer. So assume that we have a family Xi I from 1 to n, such that Xi equals Xj I J the power of n. By definition, Xi is the following fraction for some I inside of the original algebra A. And M well, M large enough. So the point is that M is the same for all i's. Then the condition is that the condition that xi is equal to xj ai aj minus 1 becomes the following condition after multiplying by the denominators. You see that I m I j k equal to yi aim ejk for any k larger. Sorry, not for any, for some k, of course. Okay, so we know that by assumption that A1 AN contains unit as an ideal in A. Thus, we can find a linear equation for 1, and we can take the kth power of this. We can take power, we can take this power of this equation, and what we will obtain is that we have 1 equal to ti im plus k for ti in A, and we can put by definition the sum of so the element x will be the sum of ti yi aik, and so this element is precisely this collation that we were seeking. So we know xi's, and now we want to collate them into one element, and we've constructed such an element. So what do we know about this element? Well, we know that if we multiply it by a in a sufficiently large power, what we get is ti yi aik aj m plus k. This can be rewritten in the following form: ti ai m plus k are aj yj. So this is equal to ajk yj. So in aj minus 1, we have x equal to aj to the power of k, j divided by aj plus k, which is in turn just yj divided by amj, which was the original definition of y. So x is indeed an amalgamation. Case. Thing we need to check is that this thing here is in fact a monomorphism. So assume that no x is 0. Linear for some x in A. We need to show that x is in fact 0. So what does it? X is equal to 0 in each of the following weeks. Then for large enough, we have AI and X is equal to 0 in A. I from 1 to. We know that 1 belongs to the ideal generated by A's. Hence, 1 is equal to some linear combination of AIs, and after raising it to the power of m, we see that 1 is equal to a linear combination of AIs to the power of m, and hence X is equal to the following sum. Since those were all 0, we get that X was 0. So it's a quite simple proof of the fact that the map E is in fact a monomorphism. And thus we've shown that O is in fact the sheaf. So we verified for each cover by principal open subsets the condition of the equalizer. Therefore, we see that O purely is a sheaf on the Zariski side. Okay. A small remark here. We have all vets is equal to this home set to A1, where A1 is a formal dual to K of X, or equivalently, it is the same thing as a home set in KH from K of X to X, where X is regarded as an algebra. Okay. So another remark is that any representable functor, like this functor, for example, representable functor is a sheaf. So this condition motivates the following definition of subcanonical Grothendieck topology. If represent resheaf is a sheaf. The largest subcanonical topology is called canonical. Let me give you an example of this concept. That we had another topology on side of topological spaces, which was constructed from open surjections. Now we will verify that any representable pre-sheaf in this topology is in fact a sheaf. Okay, so assume that we have a covering family from Qs to X, so it's a covering family for X. That means that the disjoint union of Qs maps openly and surjectively to X. And assume that we have, assume that we have a matching family. Family. It's from Y alpha, say, to Z. They all, of course, can be glued together. Simply because if we're given a function on each of Ui's and we have an open surjection, then we can define the value of this function alpha on each point of X. Now the issue is that we don't know if alpha is continuous. Let us verify that this is in fact the case. Okay, so assume that we have an open subset U and Z. We need to check that alpha minus 1 of U is in fact open in X to verify that this is a continuous function. Well, we actually have a function f from the disjoint union of Ui's. So we have the following equality of sets. So we just pull it back to the disjoint union of Ui's, and then we, so to say, pull it down to our space Fs. Okay, so since F is surjection, yeah, okay, so since F is a surjection, we have this precisely this equation. But what we need to do now is we need to use the fact that F is open. Sufficient. Check that 1 alpha minus 1 of U is open inside of the union UI. How are we going to do this? Well, we have f minus 1 alpha minus 1 of U intersected with uj being equal f j minus 1 alpha j minus 1 alpha minus 1 of U. This in turn is just alpha j minus 1 of U, which was continuous, and thus it is an open subset inside of uj. What remains is that we have to note that since each of these intersections was open, then f minus 1 alpha minus 1 is open inside of the whole UI, a union of UIs. Therefore, we've shown that, in fact, each representable sheaf in this topology on the topological set T curly is in fact a sheaf. Okay. Okay, so now we want to know that if J is any subcanonical topology, then the unit embedding factors through the inclusion of the category sheaves into the category of pre-sheaves. So we have category C and so we have this factorization. This is just the definition of subcanonical topology. Okay, now one of the principal definitions of this theory. Crossing topos. The category equivalent sheaves on a certain site. First, this site can be not uniquely defined, and obviously the condition that something is a growth-induced topos can be formulated internally. Well, it's not obvious, but it can be formulated internally, and Giroux's theorem implies the way to recognize growth-induced topoi precisely from these internal conditions. So Giroux's theorem provides a method of constructing a site based on abstract growth-induced topos. Okay, so we finish with the following proposition. Of sheaves is complete side of the category of pre-sheaves. That means that any limit of sheaves is in fact also a sheaf. The proof is straightforward. We just need to observe that since the sheaf can be given by an equalizer condition and limits compute with limits, well, we can just take, first of all, we can take equalizer of pre-sheaves, then we can pass to the limit, and we will still get an equalizer. So I think that's it for today. Are there any questions, suggestions, comments? If no, then thank you for coming.
Grish, sorry, could you explain, please?
Yes.
Maybe I skipped it. What it means to be a complete category,
It
subcategory.
just means that it has all limits.
Oh, okay. So it's just a complete category which sits somewhere. It's not another.
Yeah.
node.
So taking limits does not put us outside of our subcategory. Yes. Thank you for the question.